Let's do it. Here I am again. This time I'm talking about incremental whole program analyses in Datalog with lattices. This is a PLDI 2021 paper by Tamás Szabó, Sebastian Erdweg, and Gábor Bergmann. All right, so here's VS Code, which seems to be the IDE that all the kids are using. And so the question is, if you're an IDE, you want results fast. And of course, faster is better. So the question is, if you want to do whole program analysis, how fast can you do it? And the answer is usually not very fast. But there's a solution here. And the solution is incrementalize. You're only changing one line of the program at a time. You shouldn't need to reanalyze the whole program to get a new analysis result, right? You should only have to analyze the part of the program that you changed. And so what you should be able to do is you should be able to just basically look at the diff, see what changed in a diff, and recompute the new result. This is a diff of some dupe rules that I was writing for my ECE750-T5 submission. And you can see, of course, you remove some rules, you add some rules. In general, you have some analysis and you change the analysis, or you change the program that you're analyzing with the analysis, and you want to know what happens when you change the program. So this is the analysis that I'm not changing, not the program. But anyway. So the context here is we are wondering about whole program data flow analyses. These are slow. They take at least tens of seconds for Java programs because there are no small Java programs. We are talking about the context where these analyses are written in the declarative language Datalog, which I showed you on the previous slide. And the paradigmatic example of an analysis that's written in Datalog is pointer analysis. And so Yanis Maridakis and his team in Athens have done a lot of work doing good pointer analysis in Dupe. The current solutions for incremental analyses are ad hoc. And so there's Revisor and there's Facebook Infer. And they work quite well, but they involve a bunch of manual effort to make the analysis work well incrementally. And so the question that these authors ask is, can we do better? Can we generalize this? Can we have an analysis and automatically get an incremental version out of this analysis without having to do a bunch of extra work? That would be great. And so in their approach, they do three things. First of all, they want to know, well, is this whole thing possible? Is incrementalization feasible or is it infeasible? And when is it infeasible? Or conversely, when is it feasible? Then, 6 years ago, they had an incremental approach, Inca, I don't know. And it turns out it only worked for intra-procedural analyses, which is not that useful, but they still publish it. And I guess they now have done better. And so they have ladder with 3Ds, and this is supposed to provide us with generalized incrementalized analysis for Datalog. And so the third question is, okay, if they've got an implemented ladder, can they show us how well it works? The key technical novelty in their approach is, and it's a bit of a mouthful, novel aggregation semantics that supports incremental recursive aggregation. In simpler words, you do an analysis, you have the results, and then you want to change things. So the idea here is you don't forget anything, you just make the things that you computed previously invisible. And this enables updates. It's a bit confusing because there's two notions of time. Their analysis internally has a notion of time steps, and we'll look at that. And then you update the program, and they call that epochs. And not forgetting anything applies at the internal analysis level with time steps. And so then when you change epoch, when you change the program, then you can go on the timestamps and you can change just the parts of the analysis results that you need to change. That makes things fast. So let's give some context. And let's talk about how we can understand Datalog. All right, here is a Datalog rule. So this says that the main function is reachable. Well, that's kind of obvious, but you start somewhere. And this is a one-area relation, reach. So reach is basically a predicate and applies to a bunch of things, and it applies to the function which has name main. The way this works is that you have things on the left and you have the things on the right. And so if all the things on the right are true, then the thing on the left is also true. And let's look at this at another example. So I put the previous rule, but now I've put more rules. And so now I've said that a method is also reachable. So there's now two ways for a method to be reachable: by being main, or by being a method that satisfies the three-area relation resolve. And resolve is true if there is some receiver and some object which has a point to relation. Then there's a call to method on receiver object RCV with signature sig and inside method in-m. And in-m is reachable. So you have a method call that's inside method in-m. And then there's things like the object has to be of class, and the class has to have signature sig, and then m has to be this. And so then once you have all these conditions, then you can say, okay, well, it turns out that this obj satisfies resolve, and then everything that satisfies resolve also satisfies reachable. And the points to analysis part of their rules is, well, PT holds between var and object. That relation holds if m is reachable, method m, and m allocates variable v object O. This is singleton objects for this analysis. Then another way that you can have points to analysis is you have points to between from an object, and then you move into var from, and then that means that you points to from var to obj. If I was really caring about teaching points to analysis, I would put pictures, but I'm not. And so this is just rules, and you can formally reason about the rules. And in some sense, it doesn't really matter too much what the rules are for this particular paper. It may matter when we talk about points to analysis later. Anyway, there's another way of having points to, which says that if you have resolve and you have this and obj. This is a context-insensitive, float-insensitive, interprocedural points to analysis. All right, so how do you solve these constraints? You have an input, and they have rules, and you compute the least flick point on the rules. So you start with some initial facts, and then we solve these rules, and each rule allows you to add new relations, and you keep on adding relations until you get no more new relations. The goal here is to have something incremental. So you want to update the fixed point based on changes to inputs. And dupe, the analysis that Yannis Maridakis does, is based on souple, which is not incremental. And so the authors of this paper did Inca, which is incremental, but as it turns out, only intra-procedurally. And I think I talked somewhere about how they did some experiments, and they're like, yeah, I think it's on the next slide. Yeah, Inca is not usefully incremental, and so they tried, and they're like, okay, mini Java is this compiler that's 6.5 thousand lines of code. And they did some analyses on it, and that took 35 seconds to run initially. And then they tried to run it in incremental mode, and they deleted an assignment and reanalyzed, and that took a mean of 9 seconds, which is way too slow for IDE usage, and a maximum of 22 seconds. This works for CI use, continuous integration, but it definitely does not work for interactive use, right? CI is good, but it's not what they're aiming for. All right. So 3 problems to their approach. First is incrementalizability, which is, I think, a word that they invented. And so is this even possible? And then second, scaling incremental analyses. And third, lattice-based aggregation. And so let's talk about incrementalizability. Avalanches are scary. The thing about avalanches is that you have a small perturbation of the snow, possibly just somebody walking on the snow, or remote triggering, where somebody's walking on the snow somewhere else, or it get warm, or I don't know, you just look at the snow funny, and then it all like falls on your like head, and you get buried and you die, which is bad. So avalanche is an example where a small input causes a large effects in the world, right? And so the idea is that you want the opposite of that. They call that the principle of inertia. So you want small input changes to lead to small output changes, the opposite of avalanches. And what they do is they test this empirically. So let's see how they do that. We'll do that later. The next problem they want to talk about is scaling incremental analyses. And so why is Inca slow? Well, it depends on an underlying Datalog solver, DRED. And so what DRED does is when you have a deletion, then it invalidates all the results that transitively depend on the deleted code. And then it starts over. And you need to do this if you have cyclic dependencies. And so what they want to look at is they want to look at some way of not having to do that. Okay, the third thing is lattice-based aggregation. And so how do you merge results? This is hard for Datalog solvers. It constrains resulting analyses. It turns out that points to analysis, you can have power set based relations, and that's fine. But if you want to do general data flow analyses, this is hard. And so their goal is to support a wide range of analyses. And so they have to have some sort of solution that where they specify some constraints on the abstraction, but not too many constraints. And then you can just get merged results and things work. So lattices, I guess people don't necessarily have backgrounds about this. So here's an example of a lattice. It shows up in their paper, but I expanded it. And so you have bottom, and then you have two different classes and objects, two each. And so you have the chain O for O1. And so this is a singleton object O1. And you have all classes of class C1. And we're assuming that object O1 is class C1. Similarly, you have O of O2, a singleton object O2. And then you have class C2, which O2 is an instance of. And the thing about lattices is that you can complete least upper bounds. And so it's the question is what element is above both of those. There are some elements that are incomparable. So you can't compare a C of C2 with an O of A1. But you can compare a lot of elements. Well, you can compare some elements. You can compare the lub of bottom and C of C2. And that's, you can compute that and you get C of C2. Or you can compute the lub O of O1, C of C1, and you go to C of C1. It's the least upper bound, right? It's a thing that is greater than everything that you specified, but not any bigger than it has to be. And so what we want to do is we want to compute the lub over a variable's points to targets. You want to find something that the variable definitely points to, but you don't want to be so conservative that you say, well, it could point to everything. If you do that, then you lose accuracy and your life is terrible. All right, so the question is, do we have inertia, right? So we talked about other things a while back, but now we're moving back to this first thing. Do we have inertia, the avalanche? And so what they did was, or let's look at what that means. So they defined a notion of impact. And so impact happens when you add something to the input and you look at the output. It turns out this works especially well for Datalog. And so here's the rules that we saw earlier. And so we add something to the input. We add O.m as a vcall. And then we look at the output before we add it, and we look at it after we add it. And we see, well, we know that this is a small change in the input. Does this also result in a small change in the output? And we don't need incrementalization to evaluate this question. We just have a normal Datalog solver, and we run it on two programs. And this works because Datalog computes finite relations, unlike Prolog, which doesn't. And the solver enumerates all derivable tuples, so you have the complete answer. And so that allows you to calculate the impact. And so we have the notion of impact, and that allows us to informally define the notion of incrementalizability. And the statement is that a computation can only be incrementalizable if the vast majority of small input changes have no impact. There's a lot of words here which don't have strict technical meanings, like vast majority and small, but we'll come up with a graph. And so they have mini Java, and they generated changes, and they went and looked to see what this will do. Note that I drew a gray square in the corner of my slides, and so if you look at the slides, you have the gray square, but then that's cleverly where the image of my face is. And so you don't see the ant benchmark, but it looks the same as the others. We're not hiding anything here. And so everything runs everything has not many changes in the output, right? So you can see that the bars are mostly for like 10E1, some 10E2, right? So there are some changes that have more impact, but most changes don't have very much impact. So that's good. It's not very formal, but it's good enough. All right. So now that we know that this might be feasible, let's try to make a solution. And so they proposed ladder with 3 Ds, the incremental Datalog solver. All right. So they use an old idea, which is Datalog solver. You have tuples. When you add a tuple, you timestamp it. So you say, okay, this is the timestamp this is the tuple we get to timestamp 1, and then you add all the things, and then you try again. This is the thing we get 2. Okay, fine. And then they say their new idea is non-standard aggregation semantics. And I think I have an analogy for that, but not quite yet. We will get there. All right. The big picture is, as I've said before, in a Datalog solver, you apply rules until you reach a fixed point. And then in each iteration, you only consider the new tuples from the last iteration. And again, notice that we are talking about computing it with respect to one input. We're not changing the input yet. So iterations is with respect to computing one solution for one input. And then what they do is they calculate some notion of components, which is mutually recursive rules, and they apply rules on a topological ordering of components. It's a standard thing where you have this graph and you have some components in the graph, you want to topological sort it, but you can't because, you know, it's not a full ordering. Well, you make components and then you do the topological ordering on these components. Okay, so let's look at a computation. And so I've picked just the parts that we need for it. So here we have a bunch of time steps. In the first time step, we start with the initial facts. So this is the program. And I've shown part of the program. They have more. But it turns out we don't actually need more to make the example work. Another annoying thing about the paper is that the example is on a separate page from the textual explanation. And it's kind of a pain to not do that. But in terms of understanding what the paper is doing, it's really helpful. So try to do that when you write papers. Okay, so in the first stage, what we have is that we know that run is reachable. This is our assumption. And then what we do is we start computing points to results. So we have s, this variable here, is there's a points to relation between s and the abstract object O of s, which is a singleton object of that s is containing. Okay, there's another rule which says points to lub, and so that brings things up to the lub. And so we know points to lub, s, and O of s. Okay. Now we're going to have more relations, and so we have s1, and there's a points to relation between s1 and O of s as well, because we have s1 equals s at step 4. And at the same time, we have points to relation s2 equals s. And so that also says S2 points to the same thing S does. So what we're doing is we're taking the thing S pointed to, and now we're looking S1 equals S. So S1 also points to the same thing S does. Okay, and then we have these points to relations, and then we have a rule that says when we have a points to relation, then we have points to lub relation. So that's rule number 5. Points to lub S1 O of S and points to lub S2 O of S. Great. And now we can do some resolving. And I've covered some things, but it doesn't matter. And so now what we say is that s.proc is going to resolve to proc this session in O of S. And same with S2, right? So we have two resolved function calls for these function calls we have here in the code, S1proc and S2proc. And so we know where they go to. They go to this thing that I haven't shown you, sessions proc method. Now here we have a session count. I think it's called a session count. Let me just check for sure. It's a support count, sorry. And so what this is saying is that we have PT, this session O of S. I forgot a bracket there, but you can imagine it. And we also have reach proc. And what the support count says is that there's two ways of getting this fact. And this is actually vital to the incremental analysis working. And so what we have is we have the resolve S1, and then we have the resolve on S2, and they both give rise to the relation PT, this session O of S, and reach proc, right? So that's key. There's more in the paper, but it turns out it doesn't matter. It doesn't matter. So this is all we need to show what we're doing here. Okay. There's another thing that they use with respect to this incremental computation, or this time-based computation, and it's the notion of a timeline. And so the thing is, you keep everything that you might have known at some point, and you keep track of what is actually true at every point. And so you have a cumulative count, which records things that are newly true at every timestamp, or it records how many times you know that this fact is true. And then you have, and note that at time step 7, it actually increases reach proc twice because we know at 2x, right? And so that's also reflected by the differential count going up by 2. And then we have cumulative existence, which is whether we know it to be true or not. And we're adding this fact, so it becomes true at 7. And it may become not true at a later epoch, which we haven't talked about yet. Okay, so between each time step, we have something called the inflationary semantics, which is their big idea. And so no backsies, is that a word that people might know? Probably not, but maybe. Anyway, no retraction. And so at step 9, you might have PT lub F O of F1. So it says that F points to the singleton object F1. And then at step 11, what you now know is points to F C factory. So it's actually less strong, but it's all you know at step 11. But the point of inflationary semantics is that a fact, once true, is always going to be true. And maybe that gives you TMI. You actually get more information than you can deal with. And so how do they do that? They have filtering and a timeless view of tuples, so no timestamps. And also, they filter out intermediate results when they're writing output. Right, so you have all these things which are true at some time, like you have PTF O of F1, but it turns out when you actually get the output, you just hide that. You sweep it under the rug, and it doesn't exist. Okay, fine. So you only see the result with C of factory, and so it looks as if you didn't change anything. It looks as if you didn't do it incrementally, but then you actually can do it fast. Great. Okay. Usually say end of an era, but we're going to say start of an epoch. And so you have new input, start a new epoch. And so what you're going to do is you're going to recalculate the new state as if we had this input all along. And we're going to use timestamps and a lot to make this happen actually faster. And I think we have an example. All right, so let's say that we have this result with the original program, which I didn't show you. But then we remove a call to s2.proc. And so in the initial state of facts, that results, that's a minus, which is sort of unclear. But you remove the virtual call to s2.proc at step 0. And then you want to see how this gets reflected in the rest of the facts over time. It turns out that at step 6, then the implication is that you remove s2.proc, resolve s2.proc, and then at step 7 you remove the point-to analysis result, this session O of S, once, and reach proc once. It doesn't actually change the answer at 7 because you can still reach it through S1 proc, right? But there's a way of doing this. It's described in more detail in the paper. Needs support counts, as I said, and the timelines. You can imagine how this works. Maybe I could have presented it a bit better, but I think that you get the general idea of how it works, which is what we can do in this sort of talk. Okay, so I talked about we want to not be super strict on assumptions, but we want to have some assumptions. It is beyond the scope of this talk to explain these assumptions in any level of detail where we can understand it. So I'll just say it. And so you have this eventual monotonicity property. You have well-behaving aggregators, and you have stratified recursion. And so they say that previous approaches had stricter assumptions, so you could apply them to less. But all you need is these assumptions, and if you have these, then you have guarantees about their algorithm, which is that the fixed point calculation terminates, and this yields the minimal model. You got to read the paper to understand more. But if you have these assumptions, then you get the guarantees. Why? Because they enable this data structure. And in particular, associativity and commutativity and inflationary aggregation are the key thing here. Let's try to talk a bit about the data structure. So on the left in picture A, you have the initial calculation. And because of their assumptions, they know that when the change happens, then they get rid of that relation. And so you then get a new data structure, and you can do roll up of the aggregations, and you get a new result. And that goes relatively quickly. And how quickly? As quickly as they show in their results. Balanced trees, and you keep all the intermediate aggregates, but you change things when you have a new epoch. So the data structure only contains the thing of the current epoch, but it contains all the states of the computation that you need to get the result for that epoch. There is a formal semantics. The formal semantics is in the paper. I am definitely not going to do formal semantics in this talk. All right, so we're almost there. Now we have this system, ladder of 3Ds, and the two research questions they have are, is ladder fast enough? And does ladder use too much memory or not enough memory or whatever? I don't know. It's probably good to state it in some sort of positive. Is ladder parsimonious enough on memory? I don't know. Not my paper. All right. So what they did was they implemented ladder in open source and released it in open source and tested it on some benchmarks. And they implemented 3 analyses, a points-to analysis, a constant propagation, and an interval analysis, and 4 Java code bases from the Qualitas corpus. And they synthesized program changes. Their argument is that the program changes are as bad as it gets for incremental analysis. You could look at their data and see if you take them on their word or not. But they say, yeah, this is a legit threat to validity for our work. Fine. Okay, what changes did they make? Well, they deleted and reinserted 1,000 object allocation sites for points-to analysis. So they do the incremental thing 1,000 times. And for constant propagation and interval analyses, they replaced 1,000 numerical literals and field reads with the 0 literal. So it's like, you have 5, now you have 0. They say that this is the worst case for workload. Probably true. Yeah, probably fair enough. And so the first question, are we fast yet? So here's some box plots, and they're, log scales. And so what's the update time on the 1,000? Well, usually it's pretty fast. It goes up to like about 20 milliseconds for ant on their thing for each change. Sometimes it's very slow. Sometimes it takes like 50 seconds. So they're like, okay, look, some changes have large impact, but a lot of changes don't. For constant propagation is faster, so everything on average is below 10 milliseconds. And interval analysis is a bit more expensive than constant propagation, but not too bad. So most changes are, I think, or all changes are under 23 milliseconds. You have the initial times here as well. 23 I just kind of made up. It's actually probably more like 15. I can't read it exactly from charts. That's kind of the thing I hate about charts. It's hard to read exact numbers off them. So anyway, the initial analysis was slow. The incremental analysis was fast. And most runs are pretty fast. So, of course, some are slow. And so what they did was they looked, we had the definition of impact, right? So it's like, okay, you have the impact of a change, and is the time correlated with the impact? And so here's the graph, and they're like, it correlates to about the 1.5 power of the impact. So large impact changes take a long time to analyze. Okay, fine. Okay, the last question is ladder with 3Ds a memory hog? And so they say the memory stayed roughly the same throughout program changes. This is actually kind of hard to measure. You can kind of look at it in top, I guess, or other things with the IDE. I don't know. But at the base, it takes about 2 gigabytes, which I don't show here. And then they do this thing, and it takes up to 8 gigabytes for points to analysis, and 2.3 for constant propagation, and interval analysis 2.9. They point out that this is an interprocedural analysis, and it includes the JRE, and the JRE is big. So it takes a lot of memory. Developer workstations should have a lot of memory. That's probably fine if you're not trying to do too many other things on the computer at the same time. All right, so we have gotten to the conclusion. So what we see is that they've shown that it is possible to incrementalize static analyses expressed in Datalog, and not just pointer analysis, but also constant propagation and interval analysis. Their novelty is the inflationary aggregation semantics, where you never throw out any facts. So you're, a pack rat and you keep everything, but you only show the world the things that that you want to show them. So you have this big basement and you keep everything in the basement, but you're like, oh yeah, here's my result. And you just bring up things that you need to show people. And many analyses are incrementalizable. And ladder, this is 2Ds, delivers results in tens of milliseconds. All right. That's what I've got. Let's talk about this tomorrow. Oh yeah. Do I think this is a good paper? Yeah, I think this is a good paper. I think they do something. I think that it is a fact that most analyses are not expressed in Datalog, but they're like, look, you could express a lot of analyses in Datalog. The thing that I experienced when expressing something in Datalog is that it's hard to do future compiler things as Datalog, but if you can express it in terms of the IE, then that's useful. So that's in terms of the applicability of their work. Do they make a compelling point about their benchmarks? Yeah, it's pretty compelling. They implemented it, and it seems to run pretty fast. I thought the paper was actually not too hard to follow. I hope that my explanations were good as well. And yeah, good stuff. Let's talk about this.